People really don't seem to like needles. And our initial idea was we've got to come up with some way to move past injecting vaccines in a way that just is fast and easy and creates no biohazardous waste. And that's really why we invented this thing.
Hello, I'm Emily Schneider from the American Chemical Society. Welcome to this media briefing from ACS Spring 2023. Nobody likes needles, but they're necessary for delivering many vaccines and biologics into the body. But what if those could be puffed through the skin instead, with just a little pressure, like being hit in the arm with a foam toy? Today, scientists report steps towards making that a reality. Using powdered vaccines that don't require refrigeration and a system driven by compressed gas, their MOFF-Jet could easily deliver therapeutics against cancer and other diseases in a relatively painless way. We're joined today by Jeremiah Gassensmith and Yelini Wajchandara from the University of Texas at Dallas. Thank you for joining us.
Thank you.
Thank you for having us.
All right. So, Jeremiah, how did you get the idea for this project?
I was locked up in the house over the pandemic, as all of us were, and nothing was really working. We couldn't even get like toilet paper, but we could still. I could found out I could still order parts, and I don't know why, but I had an indeterminate amount of time, so I wanted to build a thing that could shoot moths or salt or something into the skin. I wanted to develop a homemade gene gun, and there are some good tutorials on the internet. So I just hit the internet and I started doing some research, and I built this thing. And I was shooting table salt at aluminum foil and just shooting salt around my home office. I was starting to get into trouble, but fortunately, eventually, of course, we were let go, and so I was able to take the MOFF-Jet out of my house. So I stopped shooting things in my house to the lab where, we actually started turning it into a real project.
Great. And then what were you trying to find out once you brought this into the lab?
I wanted to see what it could do. Largely, I kind of expected it to do some gene delivery. But really, what I did more or less was just kind of hand it to Yelini and say, I built this out of pandemic boredom. and now we should probably try to find something to do with it. And then Yelini really took the reins from there, and I think she's done a wonderful job.
Yes, so he after Dr. Jeremiah built up that gun, and then he gave it to me and used our expertise to do something with this. So I was also given a task that to do a deep literature dive on gene guns and how people deliver with it. And then so now we were trying to find out with the cost effective, like inexpensive delivery system, and with our expertise on like vaccine protection with MORPH, combine those two together and like delivering solid formulations through our delivery system directly into plants and animals.
We had already developed a technique for encapsulating biomaterials in a way that made them really, really tough. And we had already explored this idea for essentially allowing them to be refrigeration free. But the idea had occurred to me that this toughness is also not just a thermal protective effect. It protects the materials against mechanical strain as well. And so, these materials are super fragile, even liposomes. So we have a paper that'll come out where we'll show we can actually coat liposomes, which are very delicate in this, and shoot it out of a gun through pig skin all the way through. So, pig skin is essentially an analog of human skin. It's very similar. And you can't do that with a lot of biologicals. You can't do that with liposomes at all. They just hit the skin and splatter, right? In fact, this is what this paper is going to be on, and that will come out soon. But you put it in this coat of armor, you can shoot it out of this gun, and it'll go right through any tissue, depending on how much pressure you want to apply.
Right. Yes. And then quickly, you guys have mentioned the word MOF a few times. Can you just explain quickly what MOF or MOF means and stands for?
Sure. MOFs are metal organic frameworks. They're a class of crystalline material that connects to each other. They're porous materials typically, and essentially there's a metal and a ligand, an organic material, a metal, and it forms this matrix. And when things get stuck in this matrix, they can't move. It's like being wrapped in a straitjacket. And so biomaterials can't fall apart. They can't run into each other. They can't really do any chemistry when they're in this locked in form. But because MOFs are, well, the MOFs that we're used are very sensitive to acid, like even just a little bit of acid, like vinegar is too strong of an acid, like a little acid. They fall apart, they completely dissolve. So they're like super robust and strong, but they're really easy to disassemble, a very gentle process to remove it. And so you can basically make some biomaterials bulletproof, and then when you need to take it out, you just add just a little bit of acid and it comes right out.
Yelini, how did you investigate this with new MOFjet?
Yeah, so when I was reading, the current available gene gun is mostly used for genetic modification on plants and also some animal applications for veterinary vaccines. So first what we did, we took a gene like a DNA that encodes red fluorescent protein when it delivered into plant tissue. So what we did, we encapsulate or protect this DNA material in CIF8 polymer and then make solid material out of it, solid formulation that we can keep at room temperature without refrigeration condition. And then I optimized using a ballistic gel model that emulate like soft tissues or like plants or animals in the body. And then I used that system and optimized what are the parameters like pressure and the distance from the nozzle that I need to deliver this material. And then after doing that optimization, we protect that DNA in the MOF and make the formulation, and we directly delivered into an onion tissue, onion bulb, like an onion. And then after 24 hours, we delivered with two different gases, actually. One, same material we delivered with carbon dioxide, and then in another setting, the same material, we shoot with air that contains 0.4% of carbon dioxide. So after delivering with two different gases, after 24 hours, we saw gene expression like red fluorescence protein expressed through the microscope with the system that we delivered with carbon dioxide. And we did not see red fluorescent protein expression with the one that we delivered with air. So that's when things start like questioning and how these difference happen with the same formulations, same genetic material inside MOF, but just the difference is using two different carrier gases. That's how I started investigating it.
Great. And then what did you find out?
Yeah, then what I found out when we took the system to in vitro, not in plants or animals, and I get the MOF encapsulated biomaterial and delivered like I can with the high pressure into test tube containing water that is pH like around 7 and 8. And then when I shoot with carbon dioxide, I monitored the pH of the solution and I saw that it going down to pH 5 and then coming up. So then we realized with the one that we delivered with carbon dioxide, it lowers the pH of the media with the compound and our CIF8 is degraded. We use ICP mass spectroscopy to detect like zinc and they degrade and went into the solution, dissolving our polymer material and releasing the DNA to the solution. So that's how carbon dioxide made the process faster and released the biomaterial like the DNA, and gene expression happened with that system. And then with air, the material was not dissolved. It's still there after like 48 hours. So that's why we did not see the gene expression with the air because it did not dissolve and release to the middle. And then we move on to animal studies. The same way as the DNA, we put like ovalbumin antigen, like a model vaccine, and we delivered and we showed that there is a difference in the release. We can release the drug faster into the body, like insulin with carbon dioxide. But if we are going to use a vaccine, we can slower the release of the drug into the body just by using the non-acidic gas.
What applications would this have?
We envision this having two applications, broadly speaking. So the first one we look at its use in agriculture, which requires very inexpensive materials. But the idea of being able to shoot genes into plants is really, really powerful because it doesn't alter the germline. It doesn't go into the seeds. It doesn't make a permanent change. It just temporarily tells the plant to do something. So you can tell a plant to hold off on fruiting if you know a frost is coming. And then also in the context of agriculture, vaccinating an animal is not quite the same as vaccinating a human. You kind of want to be far away. So if you want to be separated when you don't want to approach a cow with a big needle. So that is one avenue. But in the other area is really doing delivery into people and getting rid of needles altogether as a way of putting stuff into the body. People just generally don't like needles. It's very well researched and documented that a reason there's pretty poor follow-up to vaccinations is because of this fear of injection. And we know that is now pretty well, that is known. And so there is this need to come up with a way that can do this without making needles, they have blood on them, they're biohazardous, and they require a skilled person to inject, obviously, because you don't want an unskilled person just playing with needles. And this is super easy. You don't have to be particularly clever to operate it. You load it up and point it and then push the button, right? And then that's it. And then the person can leave.
Okay, well, thank you, Jeremiah and Yelini, for sharing your research with us.
Thank you for having us.
Thank you very much for having us.
Be sure to check out our other media briefings for ACS Spring 2023, which will be posted throughout the meeting at www.acs.org/ACS Spring 2023 briefings.